So this demonstration is based on something that you've all learned a little bit about in middle school, and that's that a battery and a conductor can conduct electricity. So the conductor I have is steel wool, and as the name implies, it's made out of steel. When you send a current through something that's this small, it actually has a tendency to get bright, like a light bulb, and in some cases actually catches on fire a little bit. So you can see that that's got some sparks to it. Now it's not that dramatic because I don't have that much steel wool, so it's going to be difficult for it to ignite. But over here, this person, for some reason, decided to make a wig out of steel wool. I mean, it looks great, but I don't know if you want to go with that. Could for a costume, I guess, but it does have some drawbacks. The drawback this has is that the steel wool is so spread out, and the pieces, the individual threads of the steel wool are so far apart from each other that there's plentiful oxygen in there. And as you probably learned before, oxygen is key to combustion. So if I just take this 9-volt battery and touch it to a piece of this like I did with the smaller piece of steel wool, we're going to see a little bit of a dramatic reaction.
You cursed rat! Look what you've done! I'm melting! Melting! Oh, what a world!
That's actually kind of warm. I can feel that from here.
Not a good little girl like you could destroy my beautiful wickedness! Ah, the moon! The moon! I'm going!
That's a good look. That's a good look, all from a 9-volt battery and a little bit of steel wool. And we still got a little ways to go. There's still some of that left. So just to summarize one more time, the whole idea with this is that there's a lot of surface area which allows all that steel wool to interact with the air around it, particularly the oxygen. When you take biology, that's going to be a key factor. When you take biology, surface area is an explanation for many, many, many things that you're going to see in that class.
Who has a wish that they're going to get an A in chemistry? Maybe like something magical could give you an A in your chemistry class with doing minimal work. Maybe this will be the way to that. Looks like a genie. Genie, can you grant me a wish?
10,000 years will give you such a crick in the neck.
I wish all of my students work really hard and are studious and participate and turn their webcams on and be active. Genie, can you help me?
Excuse me? Are you looking at me? Did you rub my lamp? Did you wake me up?
What you just witnessed was the rapid decomposition of hydrogen peroxide via a catalyst, manganese 4 oxide, that made a lot of oxygen gas, creating some condensation that we just witnessed, and also generating a good bit of heat. My bottle is hot, very hot. The genie in a bottle.
Ooh, I don't feel so good.
Have you ever had something that just absolutely turned your stomach? It might be, say, failing a chemistry test, or maybe it's just eating too much Halloween candy. Well, our little pumpkin friend here had the same kind of thing happen this year after going out trick-or-treating. So I want you to watch closely. We're going to add a chemical to him and see how he reacts to that. Okay, little guy, let's see how you feel about this. Feeling okay? Are you all right?
I'm going to throw up.
You look a little peaked.
Don't throw up.
Oh, I don't think it agreed with him. That's not a good sign.
Oh, this is ugly.
Definitely not good. So I don't know if you guys can see it at home. Do you see there's actually steam coming off of it? So what type of reaction do you think that this would be? Do you recall from previous experiments? This was an exothermic reaction. It's giving off heat. And this is very similar to Mr. Roddy's experiment that he just did. It's the decomposition of hydrogen peroxide. That's what I added from this graduated cylinder. The difference in this is we had Dawn dishwashing detergent. So that's where the bubbles came from, whereas Mr. Roddy's was just the neat looking smoke coming out of the genie's bottle. But this time, because we had the soap in there, it created the bubbles.
On Halloween, as well as many other American holidays, we love to light fires. We also are obsessed with mythology about dragons, and warriors, and celebrating. And so with this Halloween experiment, we're going to set something ablaze. We have a dragon that's very hungry, and because Mrs. Harris has curly hair with flammable products on it, she always dons her PPE before dealing with the dragons. When we light a Bunsen burner, we want to make sure that we get a match lit, and then we're going to increase the flame. This is a specialty burner that is much bigger, and we are heating up a substance that will generate a lot of oxygen. Oxygen will help us burn things. And one of the things that we can burn is sugar, a dragon's favorite food, and Mrs. Harris's favorite food. So I see bubbles that are forming inside the dragon's mouth. My dragon is very hungry. Dragons love sugar. As you saw, our dragon was hankering for some delicious sucrose, a type of disaccharide or carbohydrate that you'll learn about next year in biology class. Whenever I put these gummy worms into the mouth of the dragon, so much heat was generated and light. We were converting the potential energy that is found within this food item into two other forms of energy, heat and light. And chemistry and biology, as well as physics, are all about energy and their conversions.
All right, guys, for our next demonstration here, we have another pumpkin, but this pumpkin ate something a little spicy, right? So this pumpkin is having some indigestion problems as well, but maybe of a different variety. So what we're going to be using today is this powder that we call lycopodium powder. And lycopodium powder is made of a flammable spore. And you'll see here, if I put some lycopodium out on the lab table and attempt to light it on fire, so you'll see if I try to light this lycopodium powder on fire, it'll kind of spark and sizzle a little bit, but it's not quite explosive, right? So this will light on fire and it'll clearly catch on fire, but it's not really staying on fire. It's not really a sustained fire, right? So how do we get it, how do we beef it up a little bit and make it really give this pumpkin some bad indigestion? How do we really spice things up here? Oxygen and surface area, right? We've talked earlier with the steel wool about how increasing the surface area allows more oxygen to react with that chemical. So how are we going to take this chemical and blow it up? All right. So now that we've got a fire inside the belly of this little pumpkin, let's see what's going on inside of him. Let's see if we can see a reaction here. So clearly you can see the effects of surface area and oxygen on the size of the flame and the explosiveness of it, right? So when we have more oxygen, when we have more surface area between our flammable particles, you can clearly see there's a bigger flame and a bigger explosion. And this used to actually happen all the time in sawmills. So sawmills get sawdust everywhere, and that sawdust collects in the rafters. If that sawdust falls and gets spread out and has a lot of surface area between it and oxygen, as soon as there's a tiny spark inside that sawmill's going up in flames. So always be careful with the surface area of your flammable materials, and never keep an open flame near anything that could be hazardous or flammable.
Hi everyone, my name is Mrs. Hayes and I am Dr. Frankenstein's intern. So my buddy here, if you look over, his arm, not doing so well, right? So we have these chemicals here where we're gonna make him a brand new hand. Now, I have part A, I have part B. What I need to do is mix them together. So I'm carefully, safety first, going to pour these mixtures together. We're gonna see what happens. Try not to make a mess. Stir, 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 stir. Now we need it to get the right form, so we are going to put it in our hand mold. I think the color is appropriate, and let's pour it in without getting it all over me. Don't worry, Dr. Frankenstein. Frankenstein's monster. Right. Does he have a mop? He needs to help me clean this up.
Not my job.
Trying to help him out here. Oh man. But that's okay. We're almost done here. There it goes. There it goes. Next time we'll have to add a little bit more, but I feel like that's gonna be an appropriate amount for our monster's new hand. So let's tie it up here. Good to go. It's a little harder than it looks.
What's taking so long, you silly intern?
Chemistry. We can do it. Oh boy. Almost there. Almost there. Dr. Frankenstein's hand. Aha! And there it is.
Oh, finally.
So we will let this sit and harden overnight, and hopefully by tomorrow, Dr. Frankenstein will be able to use this hand to replace the whatever's going on with his monster.
24 hours later.
Here we are back in the lab with my friend here, Frankenstein, Dr. Frankenstein, his monster, I don't know. Either way, look at this hand, right?
What's wrong with my hair?
So if you remember what we did, we took two liquids. We had part A, part B, we mixed them together in the mold, and look, a day later, we have a solid hand. It might be rotting a little bit, that's okay, because it will serve its purpose as my friends here. All right, we're just gonna, like, look, that's great, right? It's better than this one, look, look, look. All right, he doesn't need all of those fingers. It's fine. It's totally just a perfect replacement hand.
Please don't take my good hand.
Whoops. It's okay. It's okay.
Yeah, we might need a new intern. first I was afraid. I was petrified. Kept thinking I could never live without you by my side. But then I spent so many nights just thinking how you did me wrong.
And I grew strong.